Okay, in the second part of the video here for 1.6, the review, we're going to talk about logarithms and log rules. So let's recall what the exponential function says. So the exponential function, general exponential function, we're going to have f of x equals, I'm going to set c equal to 1, right? C equals c times a to the x. Well, we're going to pick c to be 1. And I just have f of x equals a to the x. I'm going to set that equal to y, and this statement here is the statement we're going to kind of work with. Well, the inverse function of this exponential function, this has a base of a, this has an exponent of x, and this has an output of y. Okay, the logarithm f inverse of x is, it's the logarithm base a of y, right? Sorry, I'm gonna come back here, put y in there, and that's gonna be an x, right? In the last video we talked about how inverse functions, they switch your inputs and outputs. You put in an output and you end up with an input sort of deal. So I've got this base again, but now this is the exponent. The output is the exponent instead of the input being the exponent. And this was sort of the result of the earlier function. This was the result of the exponential function. So output, result. Okay, so I'm going to take the result first. I'm going to put it into the logarithm. I'm going to tell you which base it was used to get that result, and then the output of the logarithm is going to tell me the exponent I would have to put on that base to get the result. So for example, let's just do a numerical example, right? Log base 2 of 8 is equal to what? Well, I want to know which exponent I have to put on 2 to get to 8. What exponent on 2 would give a result of 8? Hopefully you answered 3, right? If I put 2 to the third, I get 8. So log base 2 of 8 is equal to 3. Okay. Another thing you could think about is how many 2's multiplied together would I need to get 8? Well, you'd need 3 2's multiplied together to get 8. Sometimes that doesn't work as well. If I would say maybe log 2 of 10. How many 2's would I need multiplied together to get 10? Well, if I had 3 of them, I would only get 8. If I had 4 of them, I would get 16. So it's going to be somewhere between 2 and 3. But when you ask how many, you kind of get some semantics going on that maybe wouldn't work quite right. But if you ask what exponent on 2 gets me to 10, then you could put some number in there, like 3.1 or whatever it is. I don't know what it is off the top of my head. I have to use a calculator. But whatever that exponent is, that value, we can write it as log base 2 of 10. That is what the exponent is that I would put on 2 to get to 10. So, like 2 to the log base 2 of 10. If I asked you that question, you just tell me it's 10. Because this is the exponent I have to put on 2 to get to 10. When I put it on 2, I get to 10. Sort of silly when you say it that way, but that's how that is. Okay, and because these are exponents, we get to treat them like exponents when we do exponent rules, right? So if I have log base a of let's say p and q, right? I want to know what exponent I have to put on A to get to the product PQ. Well, because of exponent rules, if I take the exponent that I would put on A to get to P, and I add it to the exponent I would have to put on A to get to Q, right? If I'm adding exponents, that comes from multiplying values, right? So this is the same thing as saying A to the x times A to the y equals A to the x plus y. If I think of this guy as P and this guy as Q, right? The exponent I would have to put on A to get to P would be x. The exponent I'd have to put on A to get to Q would be y. If I want to get to their product, the exponent I would have to put on A to get to their product is the sum of the two exponents that I would have to get to them individually. That's how that works. And log base A of P over Q, we've got the division thing, and when you have division, the exponents get subtracted, so the exponent log base A on P minus log base A on Q. So the division corresponds to subtraction of exponents. We think of logarithms as exponents. Then I know that subtracting those logarithms is just like subtracting the exponents, so this is a logical statement here. Okay, log base A of, let's say, P to the nth power. Well, this is just repeatedly applying that first rule here. I have to have P times P times P a bunch of different times. Well, I add them up then, right? I add up that exponent n times log A of P. Okay. And those are our basic exponent rules. There's maybe a couple more that I could apply. If I set P equal to 1, the log of any number of 1, what exponent you have to put on a number to get to 1? Well, if you put a 0 up there, you get to 1, so that would be a 0. And so if you have a 1 over a q, it's just minus log A of q. So log A of 1 over q equals negative log A of q. Right, this becomes a 0 in rule number 2, and then we're just left with the negative bit there. Because these are inverse exponential functions, we also get to say that log base A of A to the x, if I put the exponential function into its inverse function, I get back where I started, right? So log base A of A to the x is x. Similarly, if I put the log function into the exponential function, so I take A, I put log base A of x into the exponential function, so that's A raised to the log base A of x power, you get x back. So those are inverse identities. And then finally I've got a change of base identity, which is really pretty useful when you're trying to find numerical values. So if I have log A of x, like maybe I had that log base 2 of 10, and I wanted to find a numerical value, but my calculator doesn't do log base 2. It usually does log base e, the natural log, which we write as ln, or it does log base 10 with the capital L log. And those two are usually the functions in the calculator. So if I wanted to put this into a calculator, I would need to somehow convert it to being able to be used by those values. So there's a general change of base form where I can change to base b. I do base b of the original input that I wanted, and I divide by base b of the original base. So that's my change of base form. So if I wanted to use the calculator, I could go ln of x over ln of a to get log base a of x, or I could do the capital log, which is base 10, right? Log base 10 of x over log base 10 of a. Okay, so you can do natural log, this is base e, right? Which is approximately 2.71828 something something something. Just a number like pi. Or this guy, this is base 10. We like base 10 because it's our decimal number system. Okay, let's do one application problem using exponential functions and logarithms. So let's say we have a population and it's growing exponentially. And we know that at time 0, the population is, for example, 100%. So we'll just put 100 people. Think of it as 100%. And at time 1, the population is 108. So maybe it's growing 8% per time period. How long until the population doubles? If you were thinking of this as interest in a stock or a CD or something, monetarily, maybe you have $100, you put it into a CD and you get 8% interest per year and it compounds. That's exponential growth. Your population can be people, it could be animals, it could be dollar bills. And so all of these doubling time things sort of have the same concept. Or I could pick, I want to know when it's 1.5 times as big, that sort of thing. Well, I come up with the equations for the exponential growth first, right? So f of x equals, where did I start? I started at 100. How much do I multiply by each time? 1.08 is what I multiply by each time. And then x is the number of times that I do that multiple, right? So this is my growth factor. This is my initial population. This is my exponential equation, right? I could find that 8% growth basically there by knowing that it grew 8 in 1 year and knowing what the original population was. So we want to know, we want to solve 200 because we want to know how long it takes before I double the population. So 200 equals f of x for x. I want to know how much time it takes to double. So we've got this equation set up. I've got 200 equals 100 times 1.08 to the x. Okay, my variable's up in the exponent, and I need to get it down from there so that I can actually answer this question, right? I want x equals some number. So right now, I've got some extraneous stuff going on. I get this 100 here and this 200 here. So I'm going to divide off by the 100 on both sides. So I have a pure exponential function on the right. So I've got 2 equals 1.08 raised to the x. And now I can write this as a different statement with logarithms. I want logarithm base 1.08 of 2 equals x, right? The logarithm's output is the exponent, so I can do that. I can write it like this. If I want now a decimal approximation, I'll use my calculator with the natural log of 2, and I'll divide by the natural log of 1.08 using that change of base form, and that's going to give me an approximation for x. I'm not going to do that, but you could plug it into a calculator and figure out what that is that way. So there's your application. There's a application for a logarithm and your review of some of the basic logarithm rules. All right, that's it for 1.6, and for the review in general, we'll have chapter 2 starting soon.